Okay, the class or the questions about the course description. So I wanted to go through this here a little bit. One of the first questions on there was to have you write down 4 of the goals of the class of AP Calculus. Okay, and so the first one was here, the reason I picked out those 4, it seemed like a little bit of busy work having to just type that out, but I did want you to be reading that to yourself, thinking about, because these are 4 that I think are especially important. Okay, students should be able to work with functions represented in a variety of ways: graphical, numerical, and verbal. They should understand the connections amongst these representations. And so we will spend a lot of time, especially the verbal. That's the part that people are not always used to in math. The explaining of answers, those kind of things. On the AP test, there is a lot of that as far as your justification for your work. Okay, so that's important. Students should be able to communicate mathematics and explain solutions to problems both verbally and in written sentences. So again, same kind of thing. Students should be able to use technology to help solve problems, experiment, interpret results, and support conclusions. Okay, the graphing calculator amongst the technology we'll be using. And then students should develop an appreciation, oh, I misspelled that, an appreciation of calculus as a coherent body of knowledge and as a human accomplishment. Okay, and that I think is really important. There are a lot of different reasons that you guys are in this class. Okay, some of you it's just the next class. You've always been good at math, and so you just kind of take the next math class, and here you are. Some of you need it for whatever job you're going to go into. Maybe you want to be an engineer, and so you need calculus. Okay, some of you, like I say, are good students. Maybe math hasn't been your strongest thing, but you're a good student. You're a hard worker. You like the AP weighted grade, on your GPA, those kind of things. Those are all good reasons and valid reasons to be in this class. And hopefully there are some, and even if this isn't why you're taking it, that you would have a little bit of an attitude of calculus is just, one of those things that is a pretty cool human accomplishment that I want to know about. And it's not going to have anything to do with what job I have and what I do, but it's one of those things that I like. Now, my English teacher used to tell me that about Romeo and Juliet and that kind of stuff, and I never bought it because I didn't like English. But that's, I probably should have. Looking back, I wish I'd have had a little more of an interest in those kind of things. Learning for learning's sake, whatever the case may be. My math teacher in high school, who had a big effect on me, one of the reasons I ended up wanting to become a math teacher, he used to always talk about the beauty of mathematics. And again, we kind of rolled our eyes and laughed when he would talk about that. But looking back, and now teaching it, I see some of that myself, especially when you get to the level of calculus. One of the cool things I think about calculus is you get to use the trig and the algebra and all the different things you've used and put together into some higher level type of problem. And not only that, but from a practical standpoint, I think it helps you get really good at those things. You'll get a lot better at your trig, and you'll get a lot better at your algebra, and you'll understand some of those things better having went through calculus. Okay? Anyway, so I do think that's an important one. Okay, the prerequisite section. Now, I had you write down 3 things that you thought you wouldn't remember or that you might have trouble with. One that showed up a lot was piecewise functions. Okay, now I think mostly that's because you haven't done much with those. They're pretty easy. We'll spend some time here early on talking about piecewise functions. A lot of people put exponential and log functions, working with those. Okay, that's actually going to be our focus today, probably the next 2 days, a little bit, is exponential and log. Some of you put knowing the trig values. I quizzed you on cosine of pi 6 the other day, right? What was cosine of pi 6 from memory, and so forth. So we're going to do some work in this IXL, and some of you will do more than others probably. But in the next couple of days, part of our homework is going to be in there because there's some good review sections on those topics. Okay? And that will be good for you because the quicker and less The quicker you can do and the less you get stuck on exponential, log, trig types of things, the better chance you'll have of being successful with the calculus. Like I told you, I think last week, many students' mistakes in calculus are not calculus mistakes. They're algebra mistakes and they're trig mistakes. Okay? And so we want to try to lessen those if we can. Those were the main ones that I saw people writing down. Okay? All right. Then we get into the topical outline. There wasn't really anything I asked about this, but these are the things we're going to be covering. Okay, these are the things we're going to learn as we go through the year. Okay, then I asked about the AP exam. Now, some of you kind of shortened this. You were supposed to kind of describe the AP exam. I mean, somebody said, part A is calculator, part B is no calculator, whatever. Multiple choice for response. That was about all you said. There's a little more to it than that. It's 3 hours and 15 minutes long. Now, Emily asked last time about the AB versus the BC. There were a couple of people who put down that the test was 6.5 hours long. That's if you take both tests, but nobody would take both tests. Okay? You're only going to take one or the other. Now, for you guys, we're all going to take the AB test, the Calc 1 test. Now, I did talk about a few students in the past who had taken the other one, which was Calc 2 stuff, and studied on their own and stuff. And, you know, I suppose if that's something you really feel strong about, you want to talk to me about trying that, you could, but usually we do not. Okay? Because if you take the BC, the one that's through Calc 2, then you get the credit for the Calc 1 one also. So you would nobody would ever take both. All right, so anyway, there's 45 questions on the multiple choice part. Okay, there's the part that is no calculator. There's 28 questions in 55 minutes. And the part B, there's 17 questions in 50 minutes. And that's where you do get to use your graphing calculator. But notice it says it contains some questions for which a graphing calculator is required. Same thing on our test. When we do a quiz, part will be no calculator, part will be calculator. The calculator part doesn't mean you need the calculator. It just means if you need it, you can use it. So quite often there are problems on there that the calculator will be of no help and you won't use it. Okay? It just means if you do need it, you can use it. And you notice the time element. These are the ones that have the most time pressure. You have 28 questions in 55 minutes. That's about 2 minutes a question. On the calculator part, 17 in 50. So that's about 3 minutes a question. So a little more time because they figure if you're punching buttons on the calculator, that just takes a little more time. Our quizzes will not be timed other than you'll have to get them done within a block. Okay? So if we take a quiz, you have to finish it in that time period. And you cannot, you guys are second block, we got lunch after, you cannot stay extra into lunch just because third block, I mean, so they are timed in that sense, right? The end of the period have to be done. Third block will not have that option of going on, and so there is kind of a time element there. Now, should be able to get done in those 90 minutes, right? Or 85 or 80 by whatever time we get started, whatever that time is. Okay. Typically, if you're not done by those 80 minutes, probably another 10 or 15 or 20 is not going to matter at that point, probably. But it's not the same time pressures here. We talked about our midterm and our final, which would be patterned after the AP test, and then we will do that. We will kind of have it timed based on these times that you see here. Okay, the free response section, there are 6 questions. 2 of them you get to use a calculator. You get 30 minutes for those 2. They have multiple parts, like a part A, B, C, and D, and so forth. So 2 questions, 30 minutes, and then part B is no calculator. You get 4 questions in 60 minutes. So it's about 15 minutes per question on the free response part. Okay, and that's what all of our quizzes are like, except the midterm and the final will have a multiple choice part. But our quizzes will be your typical math where you work out, show your work, free response type of questions. Okay, all right. On your actual grade then, on the AP test, half of your grade is based on the multiple choice. Those, how many questions is that? 45, 28, 17, 45 questions. And then the 6 free response makes up half your grade. So it's half and half. Okay. And then we talked about, there were some true-false questions. Well, no, you had to list the 4 things. Some of you missed that. Some of you said list 4 things that you can use your calculator for, and then some of you put like part A on the test, AP test. No, it was these 4 things right here. You can use your calculator to plot the graph of a function in a window, find the zeros of a function, which is another way of saying solve equations, okay, which we'll talk about as we go through the year. You can use your calculator to solve equations, which our calculator, the CAS part of it, allows us to do. Numerically calculate the derivative of a function, which one of the things we'll learn, and numerically calculate the value of a definite integral. Now, it doesn't say you can use your calculator to add 2 numbers. Well, of course you can use your calculator to add 2 numbers, right? What they mean there is you can use your calculator to do those 4 things without having any supporting work. Okay? So if it's a calculator portion of a test and you have worked it out through calculus or whatever to e to the 3x equals 14.892163, whatever. It's a calculator part of a test. You can go to your calculator and solve that equation and write x equals blank and just write the answer without showing how you solve that. That's what that means. Okay, if it's the calculator part of the test. Now, we'll also have times where we have to be able to solve that on the no calculator part. So we'll spend a lot of time learning that. But if it's on the calculator part, you can use your calculator to solve it without showing any supporting work. That's what that means. All right, and then finally there were some true-false questions. What was the first one? It said, is a calculator result sufficient? I think was the first one. Let's pull those up. Calculator result is never sufficient for an answer. Now, I meant that to be true. Some of you put false with kind of some clarification on it. Basically what that means is the example I just showed you. So you might be saying, well, guy, you just got done telling us that you could just use your calculator to get that result and that was good enough. No, the part I left out is this line would have had to been on your paper. You would have had to have some work showing that you got down to this equation. You couldn't have done that in your head or whatever, and then just put, they call that a bald answer, right? So when it's a free response type question and you just have an answer, that's what they mean by that's not good enough. There'll have to be this supporting work. So that's why that was really a true. Okay, very rarely will you have a problem where you just have an answer down. If there was a bunch of other stuff going on, especially with the calculator. Answers must be accurate to 3 decimal places, that is true. Proper calculator notation is acceptable in your problem setup in place of mathematical notation. That is false. And I think, oops, and I believe it says that word for word. This talks about students. For solutions obtained using a calculator other than one of the 4 listed above, students must show the steps necessary. A calculator result alone is not sufficient. And then here, oh shoot, why can't I? Thought I had this highlighted. Maybe I went past it. Oh, here we go. Right here. If a problem involves finding the area of a region, the area is appropriately computed with a definite integral, students are expected to show the definite integral written in standard mathematical notation in the answer. Required to write the mathematical setup that leads to that result. I thought somewhere it said something about not writing it in calculator notation, but whatever. And you'll see what we mean by that later on. Okay, so that was what I was looking for in those questions. All right, let's move on then to Appendix B. Appendix B in your book. Back in the back page there, A19, A18, and A19. So here in Appendix B, we had 2 through 5, and we had 17 through 26. And so the first ones, hopefully, were pretty easy there. On number 2, did they have something like this? Negative 10 to what was it?
Negative 15.
Negative 15.
It's just 15.
Just 15, right.
Yeah.
Okay. Now, and let's see, there's no line under that one. And then they also use this fancy set notation. You know, there was a day when we used to do this a lot more. This set notation, the books used to make us write this a lot more formal language. As you get higher up into mathematics, it's used more often. We don't use it a whole lot anymore. This vertical bar is read with or such that. So this means the solution set is all x's with x between negative 10 and 15. Or such that x is between negative 10 and 15. Now, we will not be required to write it like that a lot. It will be acceptable for you to do this. And then the notation I was really trying to get you to use there, your answer to number 2 really was supposed to be a negative 10 with a parenthesis and then a 15 with a square bracket. That's what we wanted to show. Negative 10 with a parenthesis means it does not include the left end, but it does include the right end. Okay? This is the notation we'll use a lot. So when you say all reals, another way of saying all reals is negative infinity to infinity. That's another way of saying all reals. Can you say all reals? That's fine. But negative infinity to infinity is another way to say that. And you would never put a closed bracket on an infinity. Ever, right? You cannot include infinity. Okay? You could not get there. So you would not want to do that. Okay? It could be counted wrong, as a matter of fact. Okay? So always an open parenthesis on that. All right, so that was one thing. Then on 17 through 26, here's the part that I didn't really get to talk to you much about on Friday, and the example in the book was not very good. But what's the first one there? 17, negative 3 to 9. All right, and it included both endpoints? Yes. All right, here is the absolute value notation that you would use. Okay, when we have so if you want to write down any kind of a note to yourself about this, it's something that will show up from time to time. You might remember in Algebra 2, hopefully you have some memory of Algebra 2, of solving absolute value inequality. Probably in Algebra 1 even a little bit. And you remember and or problems? And or problems would look like this, where the tails would go this way. And problems were the kind where it was in between. Well, we rarely are going to have that kind of stuff. We're going to talk a lot about intervals like this, between two numbers. Okay? And this is how they're typically written. But they can be written in this notation. And I'm not even sure in algebra class we ever talk about this, but this is how you want to think about it. Because what's the middle of this interval? What's in the middle? The whole interval is 12. 3. So is 3 in the middle? Yeah. It's 6 away from both edges. So this would be x minus 6 is less than or equal to, and now when I say the radius, so here would be negative 3, here would be 9 if we were doing a number line. 6 is right here in the middle, so what's the radius? Well, oh, whoops, I'm sorry. 3. Yeah, you guys said 3 and I wrote 6 because I had in my mind how far apart it was. Thank you. That's 3, and how far is it on either side? 6. It's 6 on either side. I call that the radius of the interval, right? The distance from the center out to the edge. We call that the radius, like it would be in a circle. So the interval would be that. It's that simple to write down. The middle and the radius. So we should be able to work both directions, right? So if I have this, well, let me just give you one. So if I give you x plus 2 less than 4, right? What am I talking about? Well, I'm talking about the middle is what?
2.
2. I tricked you. Negative 2, because it's supposed to be a minus there. It's x minus the middle. So it's -2, and then how much each way? 4. So what would this be? 2, -6. So this would be the interval from -6 to 2. Now what you did in math class, in algebra class, is you took the bar, you may remember this, you took the bars off, you did x plus 2 less than 4, and x plus 2 is greater than -4. And then you would solve each of those. So you subtract 2, you get x is less than 2, and subtract 2 here, x is greater than -6. Well, less than 2 would be this way. Greater than -6 would be this way. Sure enough, it's between -6 and 2. That's how you would have worked it in Algebra 2 class, right? As an and problem, and you would have taken the bars off and done that. Well, if you just understand that it's this x minus the middle less than the radius, it's a quick way to convert back and forth between those two kinds of things. Okay, so that's what that was. We use set notation a lot, and then of course we could write this -6 to 2 like that. Okay, so we do that a lot because think about it in trig class. When you were solving, I know right now they're solving trig equations in Honors Advanced Math. And a lot of times you were supposed to solve the equation between 0 and 2 pi. Right? We do that a lot. We say, look at the sine curve between 0 and 2 pi. So we're always, oftentimes, giving you a domain, giving you a set interval to look at. So you're going to see that a lot. Okay, let's go on to Appendix C. The thing that was applicable here, for those of you that were gone last time, is point slope form. Point slope form. Now, this we're going to write, and again, if you were gone, you want to watch the video, but we did that thing with the door opening. And we wanted to, this was a graph of the door opening. It opened, 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 slowed down, it stopped, and then it started closing again. And we wanted to find how fast was that door opening, which was the slope of the graph right at that point. That was the instantaneous rate of change. Remember that conversation? Okay, so one of the things we're going to be doing a lot this year is we're going to be finding the slope of a tangent line, or finding the equation of the tangent line. Well, this is how you find the equation of any line. You need a point and you need the slope. Okay? So in those problems, somehow or another, they were giving you the slope and giving you a point, and you should have been able to write the equation. Does anybody have one of those they want to look at, or they had a question about?
Yeah, on 31,
Yes.
I kind of forgot how to do, like, B, it's 2/5.
Right.
2/5 again.
On 31.
Yeah.
Oh, wait a minute, are you on the right page?
31,
Yes, okay. Oh.
It's 2/5.
I got you. Now it says find the equation, find the equation that lies perpendicular to this. Right. So what they give you is they give you y equals 5x plus 7. Right? It's perpendicular to that line.
So it's -1/5.
Yes. And it goes through what point? -3, 1. So here's a classic example of what we're talking about. So they want us to write the equation of a line. What do we need? We need the slope and we need a point. They gave us a point that's on that line. We need the slope of that line. So sometimes, I mean, the easiest ones, back to Algebra 1, they just tell you the slope. Okay, but that's usually not going to be the case. Somehow we have to find the slope. There'll be a variety of ways we'll find it. Here's one example. It's perpendicular to this. Well, perpendicular lines have opposite reciprocal slopes, right? So the line we're looking for has a slope of -1/5. So now I just plug into this. So I simply go y equals -1/5 x plus 3 plus 1.
See, I got that, but it says 2/5 in the end.
Okay, so they went ahead and, now, so let's talk about this, because I think I mentioned this the other day, but we hadn't seen it in action. I think I said this, you can stop here. This will be acceptable.
Gotcha.
This will be acceptable. However, in the back of the book, they often will simplify. right? They will oftentimes distribute here, which would be negative 1/5 x minus 3/5 plus 1, and then negative 3/5 plus 1 is 2/5. And so they would write it. And I know there are people, I've had people in class who just like to do that. They're used to doing it and they feel more comfortable doing that. That's fine. All I would say is it's disappointing when you have the right answer here and then you screw up something here and lose points. So be careful with that. But it is okay to stop right there. Okay? But there it is, great example. So for some reason, every year there are people that struggle when we have to write the equation of a line. And it should be a very easy thing. You've got to memorize this, point slope form. And somehow in the problem you find the slope of the line you're looking for, and somehow in the problem you get a point that's on that line. You need those two things, and then you just plug them in, and then you can stop. And there's the equation 1. Okay? All right. The golf, I also assigned that golf thing. I said that was kind of an optional deal. I was going to collect those, but I got something else I want to give you time to work on today, so we're not going to take time to do that just right now. So if you did that, that's great, and I will at some point probably collect those from you. But that was just more practice writing equations of lines. All right, what I want to do at this point is have you get out that little packet I gave you, the explorations. Okay, so we did number 1 and we did number 2 on your graphing calculator. We want to look at number 3 today. You don't have to write this down, but beginning calculus, elementary calculus, whatever you want to call it. Seems kind of weird to put the term elementary and calculus together, but you know, elementary calculus is essentially these two things. I mean, these are the two main things we're going to talk about. And the first one, the derivative, is that instantaneous rate of change that we did in exploration number 1. Okay? And so we're going to spend the first half of the year, the first half, into February, talking about the derivative. Okay? And we're going to spend the second half. Now the second half, actually, we spend less time in the second half because there's a connection between these, and so all the stuff we've learned about derivative really carries over into the integral, so we can go a lot faster, we can get into it a lot quicker with what we need, which is great because that leaves us time to review for the AP test and for our final and stuff towards the end of the year. But the second big thing we talk about is something called the integral. The integral. Okay, and what we're going to do today is go through this exploration. We're going to just kind of do it together. And we're going to go through this exploration and see see what this thing called the integral is all about. Okay? All right, so read the scenario here on exploration 3. Think about it a second. Read the first question. All right, anybody want to throw out an answer for number 1? 1,200? 1,200
1200 feet per second. Yeah. 1200 feet.
feet, right? It just feet, right? Because now, if you've been in physics class, I know in science class, they always, a lot of times in science class, they make you write down your units with every calculation. I'm not going to make you write those down. If you're in the habit of doing it, it's a good thing. But what are the Y units here? Velocity, which is feet per second. And what are the X units? Seconds, right? And so, what does your velocity seem to be between here and here? 60 feet per second. Right? So if I was in science class and was going to make you do that, you would write that down. And then times 20 seconds. Distance equals rate times time. You multiply those, seconds cancel out. 1,200 feet seems to be what we're talking about there. So we were passing a vehicle, we were going 100 feet per second. Once we got around them, we started slowing down. So our velocity graph came down. We're going slow. And we slowed down here, 30 seconds later, we've slowed down to 60 feet per second, and we're just going to maintain a constant velocity because it's a flat line, right? So it's a constant 60 feet per second the entire time. So it looks like between there and 12 feet. That's easy, that's algebra 1. Now remember when we were talking about rate of change? Average rate of change was slope between 2 points, right? But when we wanted to do instantaneous rate of change, we needed what? We needed slope at 1 point. Well, there's no formula for slope at 1 point, so what did we do? We did 2 points, but let them get really close together. We let them get really close to 1 second to see how fast that door was opening, right? That's what we did. All right, so now you go down to the next question, and it says, explain why that answer can be represented as the area of a rectangular region. Yeah. Yeah. Oh, geez. Isn't this 60 feet per second times 20 seconds? Isn't it the area underneath this velocity curve? Isn't that 1,200? It absolutely is. Now, my algebra class would go crazy if they did, well, we don't, a geometry class, let's put it this way. A geometry class would go crazy if you told them that this area was 1,200 feet. Because didn't you learn that area always has what unit?
Feet squared.
Wouldn't it be feet squared? Isn't area always feet squared? Not always, right? Not anymore. Okay? You're in calculus, right? Everything's different now. The whole world has changed, right? But that's true. I mean, we always, all the examples we've done up until now is when you do, now if you've been in physics class, you've probably done this already, right? Did you do that? Have you done stuff like this? Where you do area underneath velocity curves, so this would be very similar, okay? So that is the area, 1,200 feet is the area under that curve. Okay, so now, but again, that's just algebra geometry stuff. There's no calculus there other than that weird thing with the units, right? Now they say, what about the distance between 0 and 20? So read number 3 there. And meanwhile, I'm going to draw it here. So imagine yourself in this vehicle slowing down. Okay? So during these 20 seconds over here, in the red, we said that this area was how far we traveled, right? So doesn't it make sense that the blue area would also be how far we traveled? But what's different during that time? We're decreasing our speed. We're not traveling at a constant velocity. In physics class, everything you deal with deals with constant accelerations and things like that, so the formulas are simpler, more at an algebra level. But when you have something that's changing here like this, how in the world, what shape is that blue thing? It's like, several different things, but it really is no shape at all, right? I mean, not a shape that we have a name for, like a trapezoid or a, whatever. So the first thing I want you to understand or agree on is that that blue area would be how far we traveled. Would that make sense? That blue area would be how far we traveled in those 20 seconds. Finding that area is the problem. And this is the connection between derivatives and integrals. When we wanted to find the average rate of change between 2 points, we did the slope between those 2 points. That's easy algebra. If we wanted to find the instantaneous rate of change of this changing, the door swinging open, we couldn't do that anymore. So we had to improvise. So we took 2 points and made them closer together. We approximated until our approximation was so good, that's what we had. Well, we're going to do the same thing here. Here's a case with a constant velocity. We can just use simple algebra or simple arithmetic to find the distance traveled. When we have a changing quantity, how are we going to find this? Now what they say is they say count the squares and estimate, right? So let's do it. So go ahead and count how many squares are under here. What do we got? So what? That's 24 squares. Now how many feet is each square? Would it be 50? Each square is 50 feet. 5 seconds times 10 feet per second. So each one is 50 feet. So 24 times 50. Oh, that's 1,200. That's our same 1,200. Yeah, that makes sense. So we had here. Now let's count these squares. I got 1, 2, 3. Those two make 1 plus that maybe. That make 1, 4. This one and that.
I'd say 5. 2/3.
Yeah, 4 to 5. Let's call it 5. But you're right. We could probably have been a little more picky about that. So 5 times 50 is 250. So somewhere around 1450. I mean, clearly we traveled farther, right? It's the same 20 seconds. But for part of that time, we were going faster than 60, so we had to have traveled farther. But the main idea there is we understand how the area over there in the red gives the distance traveled, so therefore we can apply something old to this new scenario, which is the same thing we did with rate of change. This is called finding the integral. The area underneath a curve. And what it represents is called finding a definite integral. So anyway, we've already answered number 4. How much does each small square represent? So the answer to number 3, how many squares? What did we say then? 29? Is that what we ended up with?
Yeah.
24 and 5, about 29 roughly. How much does each small square represent? 50. So therefore, 1,450 was our distance traveled. So problem 5 says, those problems involve finding the product of the x and the y value. Right? We multiplied the y units by the x units is essentially what we did. That is called a definite integral. And then it talks about explain why the problem has feet for its units. Well, we did that already, right? Just feet per second times seconds. That's good enough. Feet per second times seconds, right? Would be feet. Okay? All right. So just to give you a little glimpse of that then, let's do this last one. This graph shows the cross-sectional area, y square inches. So this is square inches over here. This is the cross-sectional area of a football as a function of the distance from one of its ends in inches. Estimate the definite integral of y with respect to x. In other words, they want us to find this area. So go ahead and do it the same way. Count the squares. I'll give you a few minutes here to do it. Count the squares. Figure out what one square is worth. And then we'll talk about what that means, cross-sectional area, and we'll make sure we all understand what they're talking about. Just find the area. Count the squares. All right, how many squares? Throw out some numbers.
44.
44, 45, 46, 45, why not? They're right in between. Okay? Each one is worth, now it's 45 squares, and each one is worth 5 5 what?
Inches squared.
No? Inches cubed. This is 5 inches squared times 1 inch. The area of 1 square is 5 cubic inches. So this is 45 squares times 5 inches cubed per square. So for a total of 225 inches cubed. There, so we just did an area problem that had feet for its units, and now we did an area problem that had cubic inches as its units. What did we just find on that football by doing that?
Volume.
We just found the volume of that football. Now let's describe what's going on with this football. Let's imagine that the football, first of all, is solid, so when we slice it, because that's what a cross-section is a slice. Let's assume it's solid all the way through, so we slice it, it doesn't just go flat, okay? So we've got a football 12 inches long. Let's say I took one end of the football and stuck it here in my stomach, and the other end was facing you. And I would go in 1 inch from the tip and I would slice off. What would you be looking at? From your end, what would you see? Well, it's solid now. The football's solid. Let's make it a big chocolate football. Okay, solid all the way through. Okay, I go in 1 inch and I slice it off. What are you looking at? You're looking at a circle, a small circle. So when they say that the Y is the cross-sectional area, what you're looking at 1 inch in, you're looking at the area of that small circle. Now let's go 2 inches in, another inch, and slice it. What are you looking at? A bigger circle, a little bigger circle. So what's happening? This is going up, right? 3 inches in, 4 inches in, little bigger circle until you get where?
Start going down.
Halfway, right? You get 6 inches in, the middle, it's a bigger circle. Then we go another inch. Now we're getting to the small end again, and so they're going down. That's what this graph is representing. So by graphing those points and finding the area under it, we just found the volume of that football. Now you could do displacement, right? You could take this thing and dunk it in water, and you could find the volume that way, right? There'd be other ways to find volume. However, an engineer who's designing something and needs to know how much material it takes, he has to do a cost analysis on this thing that he's designing, and it may just be on the computer. So therefore he can't dunk it in water to get the displacement. Now I suppose it could print it on a 3D printer, right? You could do that. Or maybe it's so large, right? It's some big, huge component of some large machine that dunking it in water to find the volume is just not practical. And so having a mathematical way of finding a volume of some odd shape sort of thing that doesn't fit one of our geometric formulas might be a useful thing to do. This is called the definite integral, finding the area of the curve. So what we've tried to do, what we've been doing today, we've been mixing, last couple days, we've been mixing things up here. We've been giving some big picture stuff, rate of change discussions, this discussion about an integral, okay? Not going to be on our first quiz, right? These are just kind of big picture of what we're going to be studying and what calculus is about, okay? And then, of course, we've also been doing some of our nuts and bolts stuff like the appendix problems, how to write the equations of a line, how to do interval notation like we want to do it, okay? And so we're going to shift gears right now into some exponentials and logs and stuff like that. So let's take about a 60-second break. So everybody stand up and stretch for a second while I get organized here. 60 seconds now, no longer. Yes. Okay, you got 45 seconds left.
Can I do like 60 points?
Well, okay, if you're a little late, that's probably okay. All right. If you want, while you're doing your break here, you can get your Chromebook out. All right, time's up.
Yeah, I signed up for something. So I didn't know it.
We got on early enough.
Okay.
All right, let's get your Chromebooks out and let's go to IXL.com. 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 Hopefully, your Chromebook logs you right back in, or you change your password so you know, or whatever. That's probably our first test here, is to make sure we can get logged in. Now, it's very important. You can work problems on this website without logging in. It just limits you to 20 and then it kicks you off. And now somebody did tell me that their students, they said just hit refresh on the website and then they were allowed to do more. But that defeats the purpose, because I need to be able to track what you're doing and see what you're doing. So you have to log in for that for you to get any credit for the work you've done. Okay? So you should have, your name should show up here after you get logged in. Let me know if you're having trouble, because I do have your password and stuff. But I think I gave everybody their little sheet. Is it remembering you when you come to the website and filling it in? Okay. I mean, you would think if you click remember that it would remember you. All right. Now, where we want to go to, well, we don't need to go anywhere just yet, I guess. We're going to obviously go into the pre-calculus skills. But I would have you jot down a couple of things here. Let me show you enough stuff to help us get a start on the things we want to talk about today. The big ones, again, what I saw in those questions that you answered for me were exponentials, logs, and the trig functions, okay, and radian measure, which is a big thing that we do. So I want to start the process here of reviewing those things. So let's talk about exponentials and log first. An exponential equation is when you have a number base and an x in the power. That's what makes something an exponential function. If you have x squared, that is not exponential. It has an exponent in it, but that is not exponential. Those are called power functions. X squared, x to the third. So that's the difference. If x is in the base and a number in the power, that's a power function. Quadratic, cubic, those kind. Or square root of x, right? X to the 1/2. That's a power function. Okay? Exponential functions are ones where the x is up in the exponent and there's a number in the base. So very important you understand that. Okay, so if I had, well, let's just do a really easy one. So if I had something like this, solve this equation, right? X is what then? 3. X is 3. Now we can just do that in our head. Okay? But we can also use logarithms. So one of the things we want to make sure we can do is we can change from exponential form to logarithm form. So this is called exponential form. The logarithm form would be log, what would go down here? The 2. Now the way to remember that is that's the base. The 2 is the base in the logarithm and it's the base in the exponential. So it's the base in both places. Okay? And then what goes here? The 8. And then over here is the x, which of course would also be, we know that's going to be a 3. Okay? But we're going to get into problems where we can't just do it in our head. We don't know what it is. And so we want to be able to flip back and forth between these two. Okay, now, the other thing that we want to notice is that this year we will be using e as a base a lot. Okay? E will be the base of most of our exponentials that we deal with. Not always, but many times. So what would be the log on this one? Well, it'd be log base e of 11 equals x. Now log base e has a special name. That's natural log. We will almost exclusively use natural log in class this year. All it is a log base e. Now you may be used to, back in advanced math or algebra 2, you might have done log log on your calculator a lot. That was what base?
Base 10.
Log is base 10. We will not use that very often. Okay? We will use natural log almost exclusively. Okay? Now there's some reasons, and there's some calculus reasons why it's better. Okay? It's kind of like, let's pass that back. There's some calculus reasons why natural log and e is better than 10. You might think, well, 10 is a lot better base. I'd rather work with 10, but you'll see as we go along why. Okay, so ln, natural log. Okay, so being able to convert back and forth here is important, and you can, if you want to write a little e in there, you can, right, as the base. That's fine. Okay, all right. Now, that converting back and forth is important. The other thing I want to talk to you about then is solving an equation. I want you to be able to do it without a calculator, although some of these IXL problems may want you to type something into a calculator, possibly. So let's say we had the problem e raised to the x equals 13. Okay? This is too easy. Okay. Well, anyway, that's fine. So let's put it into log form, which would be
ln 13.
ln 13 equals x. And we'll just stop right there. Right? Now, there's no reason to go to your calculator and get a decimal here. There's no reason. ln 13 is an acceptable answer, right? And if it's a no calculator problem, you'd have no choice. You'd have to stop right there. Okay? Well, if we're going to be using ln's, and you get the problem 2 to the x equals 21, is there any easy number you can just do in your head for that? No. So let's put it into log form. What would you get? Log 2 of 21 equals x. Now, would you leave it like that? I would suggest that we would not most of the time. The problems will probably say put it in form of natural log or whatever. We will not want to have our answers like this. Now, I'm going to show you how we could solve it and make that not be an issue. But there's something called the change of base formula. Anybody remember that? Well, you did. You guys, I'm sure, always use log 10. You can do any log you want, actually. But it's log 21 divided by log of 2. But it can be any log you want. Since it can be any log you want, and I'm telling you the one you want is natural log. So we're going to change that into ln 21 over ln 2. And that's going to be our answer. That's called the change of base formula. You can change this into a new log. Now you guys probably did log log base 10 of this one divided by this one. Okay, we won't go into why that is, doesn't matter, but that's what you got. Okay, now let me show you another way though, and to be honest, I think this is probably the easier, or at least it's the more consistent way to solve these. So let me rewrite that problem. 2 to the x equals 21. Instead of changing its form, what I'm going to recommend to you is that you, when you want to solve an exponential, do the log of both sides. Does that sound familiar?
Yeah.
Do the log of both sides. Do it with natural log. So I'm going to do ln of this side, and I'm going to do ln of this side. Now, there was a log property that had to do with what goes on when there's a power inside of a log. You can bring it down in front and multiply it. And that is why using logs, that rule right there is why logs is so nice when we're trying to solve an exponential. Because the problem is the exponent's up there in the power. How do we get it out of there? Well, here's how. You do the log of both sides. You can bring the x down in front. Now we just divide by ln2. So we get x equals ln 21 over ln 2, which is the same answer we just had a minute ago. Now you might look at that and say, well, that's a few more steps. But as the problems get more complex, it gets hard to convert forms. It's easier to just do the log of both sides and then get the x by itself. So those are a couple of log things. All right. Last thing, and then we're going to get in there and let you start working for a while. Let's switch to trig a little bit. Let's talk about radian and degree measure. Pi 6 is equal to what in degrees? 30 degrees. How do you know that?
Because
Memorized it.
pi equals 180 degrees.
Here is the key right there. Pi is equal to 180. That's what you got to remember. Now I know there's a multiplication. You multiply by 180 over pi, or you multiply by pi over 180, whichever way you're trying to go. The only problem I don't like about that is just the old, trying to remember, like canceling the pi's and whatever, which one do I use? I always just think I substitute pi for 180. So if I put a 180 in here, 180 divided by 6 is 30. Now we're rarely going to do degrees. However, in this website, they do ask you about degrees a fair amount. And actually, I think that's okay here in the beginning to switch back and forth. Okay? So pi is equal to 180. So if I want to, do 5 pi thirds, okay, and convert that into degrees, right? I would probably do 180 divided by 3, which is 60, and then times by the 5, which is 300 degrees, right? Or do 5 times 180 and then divide by 3. But if you're trying to do it without a calculator, it'd probably be easier to do 5 times 180 over 3. You can just do 180, right? Goes into there 60, and then 5 times 60. Okay? And then I guess the last comment I'd make, because I'm going to let you guys kind of do some of this on your own, is the old unit circle business. Okay? Right? The unit circle, and of course this is 0 radians, this is pi halves. Pi is 180 degrees. Everything's going this way, remember. 3 pi over 2, right? Which is 180. This is 270, right? This is 90. Okay? And all those trig values and those kind of things. Now that maybe some triangles to kind of remember. 30, 60, 1/2. 3 over 2, right? And then the other triangle you're trying to remember is the 45, or the pi force.
2 over 2.
Root 2 over 2, root 2 over 2, and 1. If you can remember those ratios with triangles, then that's helpful in going through this, okay? Now, I've got a number of these for you to try. I can't, right now I'm thinking if you would go into the pre-calculus skills here, and so basically our homework for tomorrow, now you should be seeing ones that are yellow and with stars by them. Are you seeing that? If you go into the pre-calculus, go down to the B section. Are those all yellow with stars by them? There's stars by them. I guess, yeah, you got to tilt your screen enough to see the yellow probably. But if you see the stars by them, okay? Now, I've starred a bunch of them, but for right now, I would say there's 4 of them. under exponential and logs, the F section, if you will. There's 4 of them there. And under the trig, now there's 2 trig sections. I'm thinking the M section. The M section under trig, it's got convert between radians and degrees, radians and arc length, quadrants, coterminal reference angles. Those 4 I highlighted, those are pretty, should be easier and a little more basic trig stuff. But if you feel you need some work on those, I would say those would be good ones to do. But I'm really a little more interested in these down here, M7, M8, and M9. But we're going to come back to the trig stuff a little bit later as well. So I think what I would like you to do is pick 4 sections out of the M and F combined. Now I've highlighted a bunch of them, a lot more than 4, and you really need to be able to do all that stuff. So if you want to do more than 4, but the minimum that I will take for your homework grade will be 4. Now, here's how it works. Let's just pick this first one in the F section. Okay? Everybody just watch up here for a second. Does everybody understand what I'm saying?
4 total or 4?
4 total. 4 total, not 4 out of each. 4 total. Now, if you're pretty good at it, it doesn't take you very long. Okay? Now, but just watch up here for a second. So 4 total. So there's 4 highlighted in the F section, and there's about 7 highlighted in the trig section. So the M section. So F and M, and there's about 11 highlighted. You need to pick 4 at this point. Now I'm going to click on this F2, convert between exponential and log. So now watch what happens on this IXL. So it says ln2 equals 0.693. E raised to the what is 2. What would you type in there? 0.693, because there's an E down here, so it's E raised to this equals 2. So you would type in 0.693. So they start out pretty easy, right? It says, well done, woohoo, way to go. Here's a log. Now it doesn't have a base, so what do we know log with no base is? 10. 10 to the first equals 10. So we put a 1 in there. Good job. Now look at my score going up. It went up 10 and went up 19. Now to master it, you have to get to 100. Now I'm saying you should probably get, to count on your homework, the minimum you should do is 80. But they get harder, so when you get above 80, they get harder. So if I'm you, I'm going to 100. Okay? But I will let you stop at 80 for the minimum as far as what I'm going to take for the grade. Okay? So it'll go up pretty fast, and then as you start getting to it'll start getting a little more tricky, a little harder maybe, and then the points don't go up quite as fast. Okay? So M and F sections, do 4 of them at a minimum of 80 of a score. Okay? That's your homework for tomorrow. And again, you'd be a little ahead of the game if you do a few more than that. So you got the last 15 minutes you can just work. I'm sorry. Yes. I love the fact you were waiting for me. So yes, go. 15 minutes. Probably get 4 of them done. And if that's the case, then for sure you should do more. I'm not sure how long this will take, but if you miss them, then it does do a pretty good job of explaining what's going on. But feel free to ask me or ask a neighbor if you don't understand what they're saying. I think this will be the most efficient way for us to review this stuff.
So encouraging.